BESSELI function. The BESSELI function returns the modified Bessel function, which is equivalent to the Bessel function evaluated for purely imaginary arguments. The syntax for BESSELI function is Bessel x comma n, where x is the value at which to evaluate the function, and n is the order of the Bessel function. In this video, we will use Taylor-Maclaurin series sum to generate the dataset of the BESSELI function over the values of x from 0 to 6. So the equation will be BESSELI function is x to the power n times the summation of a times x to the power 2k, where a is the coefficient, 0.5 to the power n times 0.25 to the power 2 to the power k over k factorial times gamma n plus k plus 1. And our value for k is from 0 to infinity. So 13. And our value for n will be that data validation, and this will be from 0 to 5. So our orders for the BESSELI function will be 0 to 5. So 0 to 5. And we'll use the Taylor-Maclaurin series sum. Array formula, series sum of the x values raised to the power starting from 0 because 2k is 0 at 0. So 0 and an interval of 2. And the coefficient will be this range. And there is a factor of x to the power n. So x to the power n, and then multiply. So we enter the chart. We use a scatter chart. And generate the trend line. Our trend line will be polynomial to the 6th degree. That's the 6th degree. And show it as label or equation. But we will move it at the bottom. So for easy comparison with the regression coefficients. So here's our trend line equation, which is the polynomial for the Bessel I function. So now we continue with the coefficient, which is equal to array formula, starting with the denominator, that is factorial k times gamma of n plus k plus 1, n plus k plus 1. So here we have completed the denominator part. Now we enter the numerator part, which is 0.25 to the power k. And finally 0.5 to the power n, 0.5 to the power n. That's multiplied. Now we can start with 0. So we have to expand this a little bit. 1, a little bit bigger. 2, 3, 4, and 5. Next, we'll calculate these coefficients using the Linus function. To do that, we complete the 1 comma x matrix, and this should be transpose from 0 to x. So we have our rows equal to the columns. Then we complete the 1 comma x matrix, array formula of the x values raised to the power 0 to 6. Now that we have the 1 comma x matrix, we enter the LINEST data y and data x. So we will increase this a little bit. Now we can look at the different orders of the Bessel I function. At n equals 0, b0 is 1.312.98. These don't match, but we have this one matches, and this the next match will be 0.25. There's no match. Our expansion coefficients don't match to the regression coefficients. At n equals 1, so we have the Taylor, the polynomial of the Bessel I function. This is 0 because it's very small. B1 is 0.198x, B2 is 0.713, B3 is 0.556, B4 is 0.253, B5 is negative 0.0484, and B6 is 0.0 or 4.34 times 10 to the minus 3. And B2, that's our B2, our N, our second order. So our B0 is 0, B1 is 0.258, B2 is 0.735, and B3 is 0.528, and B4 is 0.225 or 226, and B5 is 0.042, and B6. Next, we go back to the BESSELI function. Here we have an example. At order 1, so we change this to 1, and the value of x 1.5, we expect this value. So we change this to 1.5. Enter. So the value is 0.981666428. That's 0.981666428. So this confirms that our data set and trend line and the polynomial is accurate because the value at 1.5 at x equals 1.5, the Bessel I function is 0.981666428 matches to our example. This completes the use of series sum, gamma, factorial in generating the Bessel I function.